Hello, we're here in section 3.7, and we're going to look at an example here where we're going to use an implicit derivative to find an equation of a tangent line. So we are going to consider the equation x squared plus xy minus y cubed equals 7. That is definitely an implicit equation there. And we are going to find the equation of the tangent line to that function at the point 3, 2. Now, if you want to verify for yourself that this point is actually on this function's graph, you can plug in the values just like you would a normal point. There's your x is 3, there's your y, it's 2. And so you'd plug in, like your x is 3 there, your y is 2, etc., to verify that this point is actually on the graph. But I'll spoil it for you. It is on the graph, and we can find the equation of the tangent line for that point. So we're going to start out like we normally would. We need to find the slope for this tangent line first. And to get the slope of a tangent line, we need to take the derivative. So we are going to take the derivative of everything on both sides of the equation here, because this is definitely implicit. Okay, so there's our left side, and then here's our right side. Okay, now let's split this up a little bit, because some of these derivatives are going to come nicely for us, like the derivative with respect to x of x squared there. That one's nice because the variable of respect and the variable in the function there match. Then some of these we'll need to use our newer trick of the implicit derivative. And then heck, on this right-hand side, derivative with respect to x of 7 is just 0. So we can go ahead and put that one right in. All right, left-hand side, that first derivative, no problem. That's going to be 2x, just like normal. But then we do hit a little bit of a more interesting issue with that second term, derivative with respect to x of xy. Well, that now is a product of two functions. X is a function, and then y, remember, y is a function of x here in this section. So we do need to take a product rule there. Product rule. Okay, so we'll do our first function times the derivative of the second plus the second function times the derivative of the first. Okay, so there's our product rule. And then on this last part here, the derivative with respect to x of y cubed, we looked at that earlier in this section. And remember that that involves the little chain of the implicit derivative, where we've got y, which is a function of x, and it is getting cubed. So y is your interior function of thing getting cubed is your outside function. So the derivative for this, remember, is 3y squared times the derivative of that inside function y. Okay, so let's clean things up a bit here and see what we've got. 2x plus x d dx of y, remember, is dy dx. Okay, and then y times the derivative of x, which is just 1, so nothing funky there. And then we've got our 3y and then another dy dx, then equals 0. Okay, so to get our true derivative here, in order to find the slope, we need to solve for the derivative dy dx. So we need to get that guy by itself on one side of the equation. So let's group all our terms with dy dx's to one side. X dy dx minus 3y dy dx. And then we'll subtract everything else over to the other side of the equation. So you can move your 2x and your y. Or vice versa, whatever it takes for you to solve for dy dx here. We're going to factor out dy dx. Okay. And then we're going to divide on both sides. So dy dx is going to equal negative 2x minus y over x minus 3y, or anything equivalent to that. If you had subtracted things over to a different side, you might have ended up with a switch in your negatives there, maybe like 2x plus y over, what would that be, 3y minus x, which would just be this expression with everything multiplied by -1 on the top and bottom. That's fine too. So if you came up with that, don't worry. And as I'm looking at this, there is a little error, which you guys might have caught as you were watching through this video. So take a glance here. If you didn't catch the error, try and see where it is. Okay, something has gotten dropped along the line here. Do you see it? It's this right here. We had 3y squared, and then in my next line, the squared didn't make it. So that needed to get carried along here. Let's go ahead and sneak that guy back in. Each one of these should just be a 3y squared. There we go. Okay, so these two require some careful bookkeeping, as you can see. And maybe don't talk while you're doing the problem so you don't distract yourself. But I gotta do commentary for y'all, so sometimes it happens. Okay, so we have the derivative here. It is in an implicit form, you'll notice. We have x's and y's in our derivative expression, but we can still use this to find the slope just like we have done in the past. Okay, we're going to evaluate this at our point of interest at the point 3, 2, which is, yes, what we were told to look at here. All right. So I'm using the Leibniz notation in this. So dy dx, and then you get that funky vertical line, meaning evaluated at the point 3, 2. Okay. And just like any other point, we are going to plug in our values. It's just now we have to plug in values for x and for y. So x is 3, plug that in. Y is 2. Okay, same thing for the denominator. All right, we've got -6 minus 2, that's -8 on top. And then we've got 3 minus 12, which would be -9 on the bottom. And we come up with 8/9. So that is our slope for the tangent line, 8/9. Okay, so you just use the derivative to find that slope. And now the rest of it flows like usual. We're going to use our equation of a line, and we're going to plug in the details. Okay, 8/9 for our slope. And we'll plug in 2 for y and 3 for x again, so that we can solve for b. Okay, and we get 2 equals 8/3 plus b, and then you need to subtract 8/3 from both sides. All right, 2 is 6/3, so 6/3 minus 8/3 would be -2/3 equals b. And that'll give us our equation for the tangent line. Y equals 8/9 x minus 2/3. And there we go. And the next video, we'll look at how to find something similar to this.